We started off with, yeah, in the sense of, we saw that signals can be classified based on the nature of independent variable time. We classified the signals into with what, continuous time or discrete time. We saw that there is another classification based on the nature of the amplitude. What was that? Analog and digital. Good. Next. Next, yes, we saw that we require one metric to determine or to measure size of the signal. How long, how, what is the breadth of it, what is the height of that signal. I mean, in a sense, to measure size of a signal, and we boiled down to an expression called as energy, isn't it? By energy also that we have seen, isn't it? Just because we are not happy with the area under the signal, we went for energy, just because it was a close indication of a energy of a typical signal. Later, we derived power and we classified the signals based on, yes, energy and power values. And we saw, I mean, we have got a very close, yes, please. We have seen an observation. We have observed something very interesting. What was that? Signals which are actually tapered, which die out after some time, are classified as yes. In fact, our voice, or maybe any practical, any practical signals, or a natural signals, say chirping of a bird, chirping of birds, or man-made, anything. So practically all the signals mostly are energy signals, but not necessarily, because in fact, to create a power signal we require an infinite duration. And we saw that signals which last long, which doesn't die out, are tend to, I mean, which somehow has some repetition or kind of regularity, then those kind of signals are classified into power signals. We saw that the signals which doesn't have any bound, which go on increasing, those are classified into as neither energy nor power. Okay. And also I've given an example to think upon. So what was that example? Let's see. So today's 27th. What was that? X of n 2 e to the power j 3n, and where j is complex number, right, for all n. Now, yes, in order to determine energy, okay, what was the formula? You go on applying the formula. You should write, first of all, how many of you at least tried? How many of you got the answers correctly? Okay, somehow you feel that it's correct. How much? Yes, that's true. So, main thing you should note is the formula. Energy first, if you calculate, what is the formula? Limit n tends to infinite. Why don't you come and solve here? Would you? Come, no problem. Yeah, so Sahil will just solve according to him. Okay. All right. Yes. Well, you don't even need to. Okay. That's good. Good. Yeah. We can even make it simple. Even simple. See, this is a complex signal, right? Of the form, that's okay. But what is generic form? R e to the power j theta. But R itself is magnitude. So the moment you write e to the power, j whatever 2 e to the power j 3 and ka magnitude, it should be 2 ka square, that is 4. And you will end up in, you don't need to write like this. I mean, that was very easy. Thanks for that, Sahil. So you should appreciate the work by Sahil. Yeah. All right. So just because it seems to be complex, but it's very simple. Answer was very simple. So now let's verify this. This was like its magnitude was 2 for all the duration, isn't it? That's why it ended up in being a power C. Okay, is that clear? Now the concept should be clear for uh, the energy signals and power signals. All right. Any person who didn't understand this, who didn't get these things, all okay? Fine. Let's move on to another topic. So fine. So first of all, we should know what we are willing to. What was our aim? Aim was to analyze or learn signals, how they interact with the systems and how they will benefit. I mean, till now, at this till this point, we didn't appreciate whatever we have learned so far. We said that okay, we defined signal, fine. We have measured the we have defined some quantity for a signal, that's fine. But what is the use? I mean, at the end, what we are willing to comparison. Yeah, I mean, this is the differentiation. I'm just telling about the differentiation of signals. So be patient. By the time after a few lectures, you will come to know what we are going to do, right? So so signals in broad way, we saw that it can be classified based on, you tell me, the amplitude, nature of amplitude, the independent variable, right? So time. Next, energy or power. So one more category called, now this is, see, signal may be anything. I may show this board to you and say that it's a signal. Of course, it's a signal. That means what? It's a graphical representation of signal. So any signal which can be anything which can be mathematically defined or can be graphically defined is also a signal. Okay. And there are two categories. If they can be well defined properly, that is called as a deterministic signal. Okay, we can determine the values easily. Say for example, x of n equal to 2m. We can, it's explicitly specified what the signal would be. Or I may show you an image saying that okay, this is a signal. I may look at the values and I can look at some graphs. Say for example, population graph of various years. Let's say in 1980s, 80s, 90s, and 2Ks. How much was the population? Around 680 around million, around 800 million. No, 1 crore and above, right? 1.2 billion and so on. So this graph itself indicates, now there is no mathematical expression for it. We can't place a mathematical equation, otherwise there will be a problem for nature, right? So we can't put any mathematical equation for this kind of signal, but although it carries some information. So signal can be classified as deterministic or random. The moment I go out, you start you start making noise. So that is, I mean, you may be useful to you, but not useful to others. Maybe that may include myself. I mean, it may not be useful to me. So that is a random signal that is not defined by graph, that may not be defined by some mathematical expression, but that is itself a signal. Maybe meaningful to you or meaningless to me, but that's itself a signal, and it is called as a random signal. Once the signal which can't be defined precisely, mathematically, explicitly, or graphically, called as a random signal. Yes, yes, good. All right. Another classification. Okay. Before that, I'll Uh, there are some more classifications. We'll come back to this point. Okay. Before that, I would like to make some points. Say, for example, now we are aware of signals. We know how to measure the size of the signal. Fine. Now in the laboratory, okay, there are some standard or specific signals, okay, which you call as a test signals, which are being used extensively in signals and systems. Let's see which signals are those. So the first signal is called a unit continuous time unit step, defined by u of t. It is defined as u of t, which is 1 at t greater than 0 strictly, and it is 0 for t less than 0. T less than 0, and it's undefined at t equals to 0. It's uncertain just because there is a discontinuity there, and it looks something like this. How does it look like? See, you have a straight line there, but it begins suddenly, right? It suddenly appears, yeah, like this, and it's 0 otherwise. I mean, not otherwise, but for negative values, and there is a clear discontinuity at value 0. So this 0, this t, this signal is u of this value is indeed 1. Alright, such kind of signal is called as a unit step signal. It's a continuous unit step signal. This signal is very useful. How? Now, yeah. Huh? Okay, I'll come to that. Now, such signals are used as a test signals. Okay, I'll come back to that later. First of all, these are some test signals. Okay, let's see. Say for example, I need to measure the efficiency of this project. I have turn this off. This one, power off. If I power it off, suddenly it stops. Right? It goes off. When I make it on, suddenly on. Right? Have you seen any projector like this? How do you remember the projector we had in the earlier semesters? Yeah. How much time it was taking? Around around 15-20 seconds, or at least 15 to 20 seconds, right? So if I want to test the efficiency of this projector, what I will give, I'm suddenly turning it on and off. Initially it was off, I suddenly put a power supply, make it on. Then I will see how this test solution, and that will determine the efficiency of power on and off. Right? So in that case, if I look at the K-on signal, okay, the earlier projectors, it was having some, the graph was appearing something like this. It was taking some time to reach at the full brightness level. However, for this Casio projector, it was very sudden, isn't it? It was like, okay, I may not say that it's like, it's like very, it's negligible, but it will be very less. So which signal is better? Which projectors are better in turning on and off? Of course this. So see, what do I mean to say is, these signals are used as test signals. Okay, so you may think of like, what is the use of this signal, like only 1 there and 0 there. So these are used as a switching, or this is also called as Heaviside function. See, many books, you may find in books that sometimes it is defined equal to 0 also. It is defined as 1 equal to 0 also. That is what we are going to consider for, see, if it is like problems, we'll consider, instead of 0 we'll consider at t, this is defined as 0 plus, I mean it's starting from 1 at 0 plus, I can say. I mean just after 0 it will start. So there is a funda of 0 plus and 0 minus in the network theory that you will learn in transient analysis. Okay, just after 0 we may say that it's going to reach a sharp value of 1. Is that okay? So this is called as a continuous time unit step signal. Now it's other components. Okay, this one is like turning on and off. Indirectly, what it is doing is there is a capacitor at the output. Okay, there is a what is called as a loading capacitor. Okay, so you might have learned in basic, electronics that the capacitor. If you give step to a capacitor RC circuit, it will take some time to get charged and so on. So indirectly, it tells you what is its time constant. You can say so RC. Time constant. It depends. If it's the RC circuit, the time constant is 1 upon RC or L by R. You remember that. So now you should appreciate that what does it mean. Okay, how much time it should take, and that those things you are going to learn in network theory. Yeah. So practically, it says how much time it takes to charge a capacitor or to discharge a capacitor. Okay, so I mean, if I simply invert this, it will be it will be used to test the efficiency of discharging or turning it off. However, for this this Casio projector, it was like very sudden turning it off. The reason behind this is like the mechanism here is LED projector. It's an LED and laser mixed hybrid projector. Unlike the mercury projector, which was lamp projector, which was taking some time to get heat up and show the complete brightness. So that was the reason. So to heat up that lamp, it requires some power to reach at the at the maximum level. That's why there was some time to reach at the maximum brightness. All right, fine. So another test signal is what is called as a unit impulse, indicated by del of t. Now this is very vaguely represented in mathematics. It's not very precisely defined. So let me tell you the definition of this. This is like very sudden, very sudden. So it's like it appears and it disappears, something like that. So it's like it's infinite at t equals to 0 and 0 at t not equal to 0. So it appears something like this. It's exactly at 0, exactly at 0, exactly at 0. So can there be any thing like any signal which exists and which disappears at the same time instant, exactly at 0? So this is like very impractical signal. You can't obtain this signal. But although it can't be obtained practically, okay, it's very useful in mathematical analysis, and we do some kind of approximation there. We define in discrete fashion also. We'll come to that later. But this signal is very useful in mathematical analysis of signal, analysis of continuous time signals, which we are going to see. Now, have you seen such function which is having only one value, okay, and it's 0 otherwise? So this is not a function. This is not a a general function. This is not a continuous time function. Not an ordinary function, I can say. So this is not an. I'll explicitly that this is not an ordinary function. What is ordinary? I mean, see, any function is not. I mean, it doesn't have any what is called as discontinuity at some point, right? I mean, it should be differentiable at some point. That is what is called as a normal function or regular, you can say. So what kind of function is this? Although we have seen that okay, this is kind of function. What kind of function it would be? So this is called as a generalized function. Okay, generalized function because it's not defined precisely. It is defined based on the effect it will have on the other signal, some what is called as a test signal or reference signal. For example, I may define this with respect to its area. That means not only this, it is also and area under this minus infinite to infinity, area under this signal is 1. That's why it's a unit impulse. Strange, right? I mean, it appears and it disappears at the same time. Its area must be 1. How can that be possible? Yeah, that's what it appears from here. So in it, in order to get to this, let's start with very basic, very basic thing. As he said, as Yash said, we may consider this signal. Consider this signal. We want area to be 1. In order to get this area as 1, huh? Huh? I'll come to that. I'll come to that. I'll come to that. I'll come to that. It's not one dimension. See, I'll come to that. That's why I'm saying that it's not an ordinary function. It actually is defined with respect to the effect it would have on others. I'll come to that. I'll come to that. So I'm saying that in order to get an area 1, let's say this is defined as some like this duration is t, and let the height be 1 by t. Is the area 1 of this signal? Is the area 1? I will evolve this signal. I'll modify this signal something like this. What should be the width and height? It has been divided by half. What is the width? T by. Let's assume that this width is t by 2. What is the height that we expect? Is the area 1? You go on. I'm saying that you go on until t tends to. Now can you appreciate the area of now? You should not say it's a single line. It's like there's very subtle point there. It's very narrow. It's such that we can't have. I mean, it's imaginary. We can't have it practically. Yeah, so that's why it's defined in this fashion. In this fashion, this is the what is called as a definition of its area must be 1. All right, although it's 0 anywhere else, this is must and is important. Fine. So what is that effect that I'm talking about? I mean to say is, now in order to define it more precisely, I would say that I will define this something like this. Let's assume that, okay, I'll go on to the next page. Let's say I'm having some signal something like this. All right, and I've simply multiplied that signal with this del of t. Okay, so it's exactly at t equal to 0. Okay, now when you do this, that means del of t, and let's say this be any function which is not discontinuous. Mind it, it's not discontinuous. It's continuous at this point. What happens? All right, so I'll draw it again. I'm saying that I'm having some function something like this. Now this function is continuous. Its derivative exists at that point, but for this function it doesn't. I mean, it's not. This is generalized function. If I do that, then I define this as in between two integrals. Okay, in between two limits as phi of. Now let this be any function as phi of t. Let this be del of t, and if I do that, what do I expect? It's only the value is here, and it's, I mean, no values at other at other instances. So it will give you the value of that signal at this point. Not only that, okay, no, I mean, see, this is a scalar, right? I can't simply put it as a scalar, so it will be into. So this is the property, but yeah, of course, now I have defined a and b. Of course, a and b should be, I mean, it should include 0. So this is valid only if this b Yes, 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 yes. So 0, this A is less than 0, less than, only then this is valid. Otherwise, you tell me it is 0 otherwise, right? If this interval is between this or that, okay, if A is, yeah,
Is pseudo is outside and be that it is automatic thing.
of course, that's what I'm, that's why I'm writing it. No, 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 okay, I'm just imposing the conditions on A and B. A and B in general can be anything, right? So that's why I'm imposing those conditions. Or I mean B if it is greater than 0, okay, and it's, or this, oh, both mean the same thing, right? That's right. All right, that means this part indicates what? A less than B less than 0 means this square, negative side, and this indicates the positive side. Okay, it's 0 in between these two. अगर मैं ये value लेता हूँ, if A and B are between these two values, then only you will get the value at this equal to 0. Otherwise, if they are if this duration is otherwise, then you won't get any value just because the impulse exists only at that space. If the impulse is shifted, then you may get the value. Now, yes, your question comes. I'm saying that if phi of t multiplied by shifted version of t minus t naught, in that case, this, in that case, this will be phi of t naught del. Is it okay? Is it okay? So this is what I mean to say. I mean, see this. Now you should tell me, okay, why I'm making this, why I'm labeling this function del of t as not a normal function but a generalized function, just because it is defined based on its effect. I mean, see, if I simply multiply, I can't get the values. I need to calculate. I need to put it under the area of a signal, right? So otherwise you may not get a sample. Now such kind of such property is also called as a sampling property. It will simply sample or pick a value of the signal at that particular time instance. All right. Yeah. No, that's why I'm saying and is important. The area, if it is 1, area, is it 1? It tends to infinity, I'm saying. So, I mean, this is not, it tends to infinite. Yes, yes, because see, if I see at the end I should get a signal, right? I'm saying that I will simply pick up that point, but this will be a scalar. I should, in order to define a scalar, yeah. Okay. Yes, I mean that means if this signal is being shifted here, and if you have a signal there, if this is t naught, you will get its value at t naught. So it will be phi of t naught. But that is only a scalar. That means the original impulse will get scaled by that value. T minus t naught. The original impulse will get scaled. See, the value here 1 doesn't indicate the amplitude but the area. Okay, that means the area will get scaled by that fact. You got it? Anyway, these are the some test functions. You will, such kind of ambiguity won't be there if you define discrete signals. Okay, I'll come to that point now. Now, okay. So the point to remember is there's a unit step signal, there's a del t's, okay, which exists only at one point. Okay, there's some relation between these two. Okay, and now I will define the relation. Now, how this del t would be beneficial practically? Say for example, this is a classroom, and I want to see how long the echo exists. What I would do? What I have done? I've clapped. Sudden impulse came, and it disappeared. isn't it? But its repercussion or its echo exists. Okay, it dies out after some time. Okay, so this can use as a test signal to in determining how the echo dies out. Okay, not step signal. I can't keep on clapping and say that okay, how to I can't determine the echo of the class or any room. That's why in theaters, now I'm giving as a homework to you or a insight. Uh, how the theaters or you go in any multiplex. Okay, how do they what kind of test signals they use? What procedure is followed in the theater or multiplex to make it eco free? There you will find such, there are some acoustic instruments where these test signals are actually imposed on, and based on the signal being received in those acoustic instruments, they'll test that how better it is in absorption of those signals, echoes. Okay, that is how these signals are used. Okay, this is for further learning. Now there's some relation between u of t and del of t. The relation is del of t is simply first order derivative of u of t. Now this you may not directly appreciate. I'll tell you how you can appreciate this. Okay, how you can assume that no, there is practically what I will get. I'll get such kind of signals. Unit step, there will be some kind of delay. Let that delay be tau. Let this be 1. What if I differentiate this signal? Can you tell me its differentiation? Huh? What is this? How can we define this? This is a RAM. Huh? Huh? What is the slope of this? You tell me. Huh? Yes. Yes. So that how it is defined between these two? I mean, how it is defined 1 by tau, no? Between what duration? 0 to tau. It is like a ramp, right? What is the derivative of that? 1 upon tau is what? Constant term. You take it out. What remains? So what is 0? Huh? No. What is what is the differentiation? That's what I'm saying. What is the differentiation? It will 1 upon tau, because what is the slope of this? Slope itself is yes. So it will be 1 by tau. What place? Till what point it will be 1 by tau? This tau is this tau. This is if tau tends to 0, that turns out to be an ideal unit step function. Okay, and if this appears to be an impulse function. Okay, if tau tends to 0, this will tend up to, and let this be u of some u tau of t. If tau tends to 0, then it will be u of t, exactly, ideal signal, and also this will be an impulse signal. That's how it is defined. I mean, del of t equal to the differentiation of the unit step signal. Is that okay? How can I define this now? Inverse is also possible. U of t is what? Minus infinite to t del of dt. Right? See, don't worry about this. Okay, if you are feeling like being heavily bombarded. So don't, this is not, this is very easy. Now equivalently I can define the signals in discrete domain. There we won't have such kind of ambiguities. Discrete is like very simple. Now test signals in, so I'll define discrete time unit step defined as u of n. Now this is very simple signal, u of n, it doesn't have any ambiguity, it's 1 for n greater than or equal to 0, it's 0 otherwise. So it's very simple signal, something like this. Now it's exactly 0. I'm saying that it's exactly 0 at other points. It's not undefined, it's 0. All right, so this is 0, 1, 2, 3 and so on. This is n, this should be 1, this minus 1, minus 2, minus 3 and so on. You got it? Now this is having close relation with this analogy with the continuous time unit step signal. Okay. Similarly, del of n discrete time unit, this is called as unit impulse, is defined as 1 only at n equal to 0 and 0 otherwise, n not equal to 0. Now this is well defined, isn't it? This doesn't have any kind of ambiguity. Exactly like that. At 0 it is 1. So this is del of n, this is u of. Is that okay? Rest is 0. It's 0. 1, 2, 3. What? No, this is discrete. That's why I'm saying that there's a differentiation between discrete and analog. We won't have such kind of ambiguity. We have that ambiguity only in continuous time, not in discrete time. Yes. It's of course possible. No? You can simply see there is only one impulse. All the digital signals are like that. It's possible. I mean, like, oh, okay, I got it. Now I'll simply define it as some values being stored in the computer. That's it. If you want to generate it, of course there will be some kind of minor delay and it will appear like something like this. Okay, but of course it won't have infinite duration, infinite amplitude. They are simply pulses. Pulses being saved. You can consider these as some values being stored in a computer chip also. All right. What is the relation between these two? You tell me. How can I obtain this signal from here? Okay, before that, yeah. What if I keep this signal? If I shift this signal one step right, and I subtract that signal from the original signal, will I get this signal? I'm having this signal. I've shifted only one step towards right. There won't be any signal here. I simply subtracted those two. There will be only one impulse here. Is that possible? That's why it is defined as del of n u of n. Now you will see now that this u of, what should I write it here? Y minus. All right, but why minus? Why not plus? That you bugged it up, yeah? Why? Yes, when you put 0 value here, okay, when n is 0 here, what is the value? What if n is 0? So n value, if it is 0, the minus 1 value will appear there. If n is 0, the new value will be u of minus 1. No? That means at n equal to 0, minus 1 value is getting appeared. That means the signal is shifting towards right. And that's how transformation of signals are defined that we are going to see now. All right, so this is the relation of, all right, del of t with del of n with u of n. And tell me about u of n, how u of n is related. U of n, yes, del of n minus, you can say it as k, some integer where k is ranging from, tell me, that's it, simple. How many of you didn't get this? Okay, what I'm saying is, did you get this? All right, no, okay, fine. I'm saying that this is u of n defined from 0, 1, 2 and so on. It's 0 otherwise. How can I obtain del of n from this signal? Del of n is only defined at 0. How can I obtain only using u of n this signal del of n? How can we obtain that? U of n, keep it as it is. You shift this signal one place towards right. That means it will be 0 here. It will begin with from 1. You subtract these two. You subtract these two. You will get this signal. This fine. Now you consider this signal. What if I need to get this signal back? I need to replicate that signal from 0 onwards towards infinite. That means this has to be taken for 0 plus del of 1 plus del of 2 and so on. Not to 1 and 2. Wait. N minus 1 plus del of n minus, this 2 and so on. Because if I define del of 1, I mean that will be 0, right? That you need to add it up till infinite, right? So it turns out to be k equals to 0 to infinite n minus k. That will give you, is that okay now? What? This one? That should be what? Yes, this should be n. Yes. Because that will be otherwise a scalar. That will be otherwise a scalar. Del of n. Yes, you are right. Why not del of 0? That will be a scalar, right? We are actually defined signals and we are adding them up. Otherwise, you will at the end you will get only one value, scalar. 1 plus 2 plus 3 plus 4, you will get what? One value. Let's say 10. If I add 1 and 0 otherwise, 2 and 0 otherwise, 3 and 0 otherwise, you will get a signal, right? Got this? Clear? Sure? Everyone? Fine. Alright. So that's how what is called as transformations are defined. Let's come back to that. Transformations. Of independent variable. What is the simplest transformation? If x of n, first transformation, as we have seen, is shift. So if it is x of n, it may get shifted to x of n minus k, or x of t. I'll make it as n naught, just to keep it consistent. And x of t, in continuous time, it will be x of. Now, if I take this x of t minus t naught, if this t naught is positive, if this is positive, right shift, or it's also called as a delay, isn't it? Because see, if this signal if this is a signal, it is being right shifted by, let's say, 2 time instance. Let's say it is 2. So this is defined as u of t, this is u of, okay, this is being delayed by 2 time instance, let's say 2 seconds. So it is starting after 2 seconds, right? If we take the time axis from left to right, okay, that is how the time proceeds from minus infinity to infinity. From 0 to it is starting after some time, after 2 seconds. That's why there is a delay. So if you find this to be positive, it's right shift and mark it as a delay. If this t naught is negative, left shift, or it's also considered as advance. For example, this same signal I'm shifting towards left. Let's say again -2. It gets shifted to -2. Okay, it got advanced by 2 seconds. I mean, if there is some event, if there is a class, if some person comes sits here at 8:45, if the class is meant to be at 9, it's an advance, right? Coming in advance. If someone come late, so it's like delay, isn't it? So it, Anna, Rohit. Okay, so it doesn't mean anything to you. I'm just giving an example. All right. So this is simple operation of time shift. Another operation. Have you learned this? Do you know these things before? Should I give the problems? Should I skip this? Okay. Another thing is scaling. You will do a lot of this stuff in this. I mean, now you should appreciate what we have learned in math is not like, it is not like no, something that which is not being used. Okay, it's not useless. It will be useful here. Scaling, it is defined as if x of t, it is defined as x of at. If a is positive, I mean, this is greater than 1, of course it should not be 0. If it is greater than, if it is 0 means again it's a scalar. If it is greater than 1, x of t is compressed. Compressed. If x is less than 1, I mean in between 0 to 1, it's a fraction. Expanded. Oh, didn't get? All right. Got it. Okay. Oh, I'll come to that. Don't worry. So if there is signal something like this, this is some signal x of t. If it is x of 2t, that means what? Put some values there. T. Let's say t equal to 1. T equal to 1 value, this, this, let me write that. So, this, wait, let me draw it first. I'm saying that the current value, okay, the current value, let's say, this 2t, I mean, it gets advanced by, I mean, if it is 1 second, if t is, let's say, 1 second, it at 1 second it will play the value at 2 seconds. If it is 2 seconds, it will play the value of 4 seconds, and so on. That's why it's getting compressed. If it is 1, it's no, at this point at 1 it will play the value of 2. If it is 0.1, it will play the value at 1, and so on. That's why this overall signal is getting compressed. 0 to, thumb rule is जिनको रट्टा मारना है, divided by the scaling factor. That's it. I mean, sorry, yeah, divided by the scaling factor a. That's it. Divide the time axis by the scaling factor. Easy. If t equal to, okay, see, you should not go for mugging. When t is 2, sorry, t is 1, t is 2, let's consider these values. T at 0.5 and so on. If t is at 0.5, what would be x of 2t? That means at 0.5 duration, at 0.5 instance, you must have the original value of x of 1 here. If t is 1, that means at this point you must have the peak at x of 2 instance here, and so on. Got this? How many of you didn't get this? Okay, I'll come back to that. I'm saying that repetition is good, no problem. Let's take some nice simple example. 0 1 2 3. I'll take another 4. Okay, if this is the signal, it is defined only between these two and it's 0 otherwise. So it's 0 0 0 and so on. So this is x of n. What I'm saying is if it transforms to x of 2n, it is getting compressed. It is getting compressed. Why? If n, let's say it is 2. If n, let's say it is 2. What is x of n? X of 2n, sorry. X of 4. That means at n equal to 2, at n equals to 2, what is the value that we have? X of 4 value. That means at n equal to 2, where is 2 here? No? I will have the value of 4. This will get, this will get here. This will compress, yes. Okay, I'll come to that. I'll come to that. So you are saying that I can't see these values will disappear because there is no such instant of n equal to 0.5. N is strictly an integer. N is strictly an integer. So I can't say that. Okay, you may now ask why didn't I consider n as 0.5? So that's an integer. I can't take that. I can only consider n as 1, 2, 3, and so on. So if n is 2, at n equal to 1, x of 2n is what? That means at n equal to 1, this is what? Okay, so it will be something like this: 0, 1, 2. At x equal to 1, the value of 2 will be there. This will be this will be here. It will be, this alternate samples will get cancelled. Okay, this will get sampled. This will get removed. Another example. Take this signal. X of 2t, what I'm saying is x of 2t would be like this: 0 to 1. Why? You go on calculating x of 2t at t equals 2. Now calculate at what point do you want to calculate? Let's consider the peak value, no? This value. Let's say at t equal to 0.5. What is the value of 0.5 at t equal to 0.5? X of 2 into 0.5, no? It will be x of 1. What is there at x of 1? Let's say some amplitude as 2. That will be here. So at 0.5, value will be at 2. Thumb rule: if it is greater than 1, okay, compress the signal. If you want, it's very hectic to do like this. This is just for understanding. Divide the axis by a. So it's like dividing the axis by a. See, 2 is divided by 2, 1 is divided by 2, and so on. All right, you understood right now? Not by remembrance, by a concept. Huh? Anyone who didn't get this concept? I'll repeat, no problem. Got it? Sure. I'm seeing some blankness. You got it? Sure. Jessica? Chaitanya? Sure? Not sure. Want me to understand? Want me to give some another example? You want me to? One example? One more example? No problem. You tell me, okay? Which example, which signal I should consider? I'll consider some one different signal. Let these values be 2 and 4. This is normal signal x of t. What is x of 2t? In order to calculate that, I need to first find now x of 2 मतलब 2t ये सिग्नल फाइंड आउट करना है. मतलब अलग अलग t के वैल्यूज के लिए ओरिजिनल ये जो नया सिग्नल बन रहा है उसके क्या वैल्यूज रहेंगे ये कैलकुलेट करना है. दैट मीन्स फॉर ईच एंड एवरी वैल्यू ऑफ t, लेट्स से फॉर 0.1, 0.5, t equal to 1, t equal to 2.5, t sorry 1.5, t equal to 2. Let's go on calculating these values. Okay, now at t equal to 0.5, what this new signal is expecting, new signal is the same thing but scaled by some factor. So what is that? X of 2t, how much it is? X of 1. That means new signal at t equal to 0.5 will be x of 1. X of 1 क्या है? Original signal. This new signal. This new signal at t equal to 0.5. Where is 0.5? This is 1. This is 0.5. Here is 0.5, right? 0.5, 1. This is 1.5. That is what we have defined, right? 2. What is the value that we have got of new signal at t equal to 0.5? X of 1. What is x of 1? 1 कहाँ है यहाँ पे? यहाँ पे है ना? X of 1 क्या है यहाँ पे? What is the value here? 2 ना? So at 0.5 the value will be 2 here. Similarly, if we proceed, tell me the value at t equal to 2. X of, what is the value at x of 4? 1. यहाँ पे ना, if you go on continuing, you get something like this. What is this signal? It is a compressed version of the original. Alright? Is that okay? अब समझा? और एग्जाम्पल दूं? समझ गया? सब कुछ समझ गया? Okay. हर बार okay. It's compressed only if A is greater than 1. हर बार नहीं. A in general मैंने treat किया. अगर A greater, now homework for you is to consider when A is between 0 to 1. Homework for you. Now